All right. Okay, so today we are going to discuss a very important topic, um, which is the chain rule. The chain rule. So today is second. All right. So what was the chain rule in one variable?
ddx of f of gx is f dash gx into g dash x.
All right. So you had in one variable, you have f from R to R, and of course, an interval or an open subset of R is good enough. And you have G here. Then you are looking at the composition, G compose F. So the derivative of G compose F is G prime Fx times F prime x, right? Provided so F and G differentiable on R. So once this is given, it is very easy to write down the derivative, right? So this was interesting, of course, and this was very very simple because you just need to multiply two number, right? Now things change in multivariable, right? So what is the, so we want to see the analog today. We want to see the analog of one in multivariable, many variables, right? So what would be a guess? Hmm? So what we need is we assume f same as like this. So let's see, f is from Rn to Rm. So let me draw the picture rather than this way. So you have Rn to Rm, and then let's say Rk. So this is F, this is your G, and you want to look at this composition, G compose F, right? So first of all, F and G are differentiable, and so what about differentiability of G compose F? Will it be differentiable first of all? What is your guess? Yeah. So given F and G are differentiable, so what about the differentiability of G compose F. So, what is your guess?
I think yes.
Okay. So, what would be the right candidate for the linear transformation?
If derivative of f is given by lambda f and like the linear transformation is lambda f and the derivative of g is given by the linear transformation lambda g, then the
Yes.
candidate may be lambda g
Lambda G
of lambda f.
compo- composite lambda. Right. Yeah. So, actually, this is correct. So, this is the right candidate. So, so a notation, a notation. So if f is differentiable at a point a in Rn, then the derivative, which is the linear transformation, is denoted by df at a. All right. So we'll use this notation. We'll use this notation for the linear transformation. We'll not use u, mu, or lambda, whatever. So most of the cases we'll use this part, this thing. Okay. So let me write the precise statement of chain rule. Precise statement. Statement. Statement supposed to be precise. Statement of chain rule of the chain rule. So we of course we need differentiability of f and g. So suppose f r into rn is differentiable at a in rn and g from rm to rk is differentiable at f of a. Then the composition G compose F is differentiable at A and D of G compose F at A is D of G at FA composition DF at A. So this part, this is a composition of two linear maps, right? Well, today we'll just give a proof of this one. So before giving the proof, let me give you an exercise in linear algebra. Perhaps you have seen it. So will be using linear transformation all the time. So this exercise would be good. So suppose T from Rn to Rm is a linear transformation, then show that there exists a number m greater than 0 such that norm of Tx is lesser or equal to m times norm of x for all x in Rn. Have you seen this exercise? Yeah. Have you done this
I
exercise?
don't think so. I don't remember doing this exercise.
Then it will be good thing to do. So you know how you represent a linear transformation in terms of matrix, right? Yeah.
Yes, yeah.
Yeah. So you use a matrix representation of T, and using the entries of T, you
Using
find
that?
the M. Okay. Using the entries of the matrix, you first represent T in terms of matrix with respect to, let's say, standard basis,
Hmm?
right? So it would be enough to consider x goes to that matrix times x, and so that this happens for that matrix. That would be good enough.
Okay.
Okay. Now there you can actually use the entries of the matrix to find the number m. All right, and you will see later this is actually is defined to be continuity of a linear transformation from even infinite dimensional vector space also. So for Rm, any linear transformation becomes continuous because of this. So this is a defining property of continuity for a linear transformation in general. So from even from infinite dimensional uh, vector space with you won't need to have norm. So infinite dimensional norm linear space, norm linear space. So this is a very important property. You must do this exercise. All right, so we'll use this here. Okay, and if you can't do, or if you have any problem in doing, just let me know. Okay. All right. So next we just give the proof of chain rule. We'll see a lot of application of chain rule, but proof is little bit of analysis, and the proof is as a proof I'll give is as it is given in Spivak's book. So this is from Spivak's book. Okay. Sorry. Assume A is already there. A is a point already there in Rm. So you assume B to be f of A, and lambda to be the derivative of f at A, and mu to be derivative of g at fa. Okay. Define a couple of functions phi x to be fx minus fa minus lambda times x minus a. Okay, it's simple. Just the expression on the top of the limit, right? You just take that to be a function. From where to so where to where this function from?
Has to go from Rn to Rm.
Right, Rn to Rm. Right. So and similarly we define psi y, which is gy minus gb minus mu of y minus b. Right. So psi is from where to where?
Rm to Rk.
Right, Rm to Rk. So here phi is from Rn to Rm and psi is from Rm to Rk. All right. Now these are of course the numerator of the limit, uh, limit which actually goes to 0 gives you the differentiability. All right. Now we consider this part g compose f x minus g compose f at a minus. So I want a candidate. So what was the candidate? Mu compose lambda x minus a. Right. So we want to show that this norm of this divided by norm of x minus a tends to 0 as x tends to a, right? So we want to look at the numerator of that one. So we want to show, basically we want to show, let me write it, limit x tends to a norm of this by norm of x minus a equal to 0. So this is what our target. All right. Now let us look at this. What does numerator gives us? We need to unfold few things. Minus mu compose lambda x minus a. So this one g compose f at x, and this is g of b because fa was b, and this one mu of, here I put something, see, lambda time x minus a is, you take lambda time x minus a this side and phi to be this side, right? So lambda times x minus a is equal to fx minus fa minus phi x. All right. So this is fx minus fa minus phi x. Right. So check that again from here, right? Okay. So now let's look at this. G of fx minus g of b minus mu of fx minus fa plus mu of phi x. All right. Now what is this part? What is this part? What is this part in terms of psi or phi?
Phi of fx.
Right. psi of fx. Psi of fx, right? Plus mu of phi x. So what do we need to show? We need to show that norm of psi of fx plus mu of phi x by norm of x minus a tends to 0 as x tends to a. All right, this is what we need to show. We will use triangle inequality here and show that each term actually goes to 0. All right. Now let us look at from the definition of psi and phi. So from the definition of phi and psi, we have and the differentiability of f and g, we get that limit x tends to a norm of phi x by norm of x minus a is equal to 0. Call this 1. We also get limit y tends to b norm of psi x or psi y by norm of y minus b equal to 0. Right? Is this clear? We get 1 and 2. Did I give any number? Not yet. Yeah? This is because differentiability. We take this as the numerator, right? And denominator is x minus a here and y minus b here. And that limit should go 0 because a is differentiable at a and g is differentiable at f of a, which is b. All right. So now, first one, consider the following. Norm of phi of mu of phi x by norm of x minus a. Right? Now this one we use, the exercise mentioned before the proof. Right? So mu is a linear transformation. So we have, there exists m norm of phi x by norm of x minus a. Hence, for some, this is true for this is true for all x rn minus a, let's say. We don't want a here. For some m greater than 0. Hence, limit x tends to a norm of mu phi x by norm of x minus a is less or equal to limit x tends to a m norm of phi x by norm of x minus a, and this is 0 by 1. Hence, limit x tends to a mu of phi x by norm of x minus a is 0, right? So we just used the exercise here, and we had the other part, right? So now we need to see this was this one. Let me call this as a star. So now you see this part actually goes to 0. So what we need to show is this part goes to 0. All right. So let's look at, so to show, limit x tends to a, norm of psi of fx by norm of x minus a equal to 0, right? Now we need to look at certain estimates here. So first of all, from 2 we have limit fx tends to be norm of psi fx by norm of fx minus b equal to 0. Is it correct? Yeah, is it correct? So what is 2? 2 is this one, right? So where does this y belong? Y belong in Rm. All right. So which you have chosen a particular direction for y, or maybe collection of directions which are actually written in terms of fx. So in the image of f, we are going towards b. All right. Is this fine? So this is actually certain particular directions. It might not cover all the direction, but it will cover some directions because we know fa equal to b. Is this
Sir,
fine?
could you
Yes.
please explain why this will not cover all the directions?
It depends on the range of f, na?
Oh, yes. Okay.
Right? So suppose a range of f goes to, let's say, R3 to R1, one dimension, and you map, let's say, something like a small digression here. So if you consider, this might not cover all the direction because you can look at f from R3 to R2 given by x, y, z to x comma 0 comma 0, right? And here for g from R2 to R, let's say uh, g of x y is x square plus y square, right? So you get one direction. If you go in the range of f, you might not get the all direction. You might not get two directions here. Yeah, is this fine?
Yes, sir.
Okay. Okay, so fx, the image of f may not cover all the directions. So here, image of may not cover all the directions. Let's say to approach 0, whatever. Now we want to show we want to see this one. So we have this limit to be 0 because we are looking at certain particular directions. Now this limit, let me write it in terms of epsilon delta. So for every epsilon greater than 0, there exists delta prime greater than 0 such that norm of psi fx Yeah, less than, so norm of fx minus b less than delta prime implies norm of psi of fx is less than epsilon times fx minus b. All right. So this is 3. We didn't call 3 yet, right? Yeah. All right. So next we will estimate this one again. Right? So now let's look at this norm of fx minus b, right? So which is nothing but, so fx minus b, so fx, which is fx minus fa, right? Now let's go back here, go back to the function we defined, this one. Let's see, fx minus fa is equal to px plus lambda times x minus a. So this is norm of px plus lambda times x minus a, lambda of x minus a, right? Now this one is less or equal to, by triangle inequality, norm of phi x plus, and using exercise and using the previous exercise. So there we get some m tilde, norm of x minus a, right? So this is 4. Now we, from 3 and 4, we have norm of psi of fx by norm of x minus a is less or equal to norm of phi x by norm of x minus a. So here we are actually getting a small neighborhood of x. And you see this, oh, I need one more thing, which is continuity. This is absolutely fine, but then for which x this is true? So since f is continuous at a, so derivative implies continuity. So for delta prime greater than 0, there exists delta greater than 0 such that norm of x minus a less than delta implies norm of fx minus b less than delta prime. All right. So we will take this neighborhood. All right. So this one we have on mod of x minus a less than delta implies this plus, oh, so there is an epsilon m tilde, right? Norm of x minus a gets cancelled. So epsilon was chosen arbitrarily, right? Epsilon was chosen arbitrarily. So we get, yeah, epsilon was chosen arbitrarily here. For since this was true for every epsilon, since 5 is true for every epsilon greater than 0, hence limit, well, not 5 is true, the everything is just 3, 4, 5, yeah, 3, 4, 5 are true for every epsilon greater than 0, hence limit x tends to a norm of psi of fx by norm of x minus a goes to 0, right? Already we bound in terms of epsilon. So it is already, we already proved. Hence, d of, so hence what? Hence we get if g compose f is differentiable at a, and d of g compose f is dg at fa compose df at a. All right, so we'll see a lot more applications, or a lot of applications of this chain rule later, from next class onwards. So we'll be in chain rule for some time. Okay, so we'll let's go to this exam. So I'll upload the questions. Okay. So and once you see the questions, then you can live after that. All right. So first thing is stop recording.